Good afternoon, and thank you for giving me an opportunity to speak in this forum. Today, I'll first go over popular methods for thalamic nuclei segmentation based on three MR modalities: diffusion, function, and structural MRI. Then, I will briefly talk about deep learning and multimodality imaging, which are emerging methods. And finally, I'll cover some technological breakthroughs needed and leave with points to ponder. Diffusion-based methods could be either based on microscopic properties of the diffusion tensor, such as the angle of the dominant diffusion direct orientation, or it could also be based on clustering the ODF coefficients, which are derived from CST, as shown below. They could also be, however, based on microscopic information. On the right-hand side is the famous Barron's Atlas, which is part of FSL, where this probabilistic tractography was done from 7 manually delineated cortical regions, so the motor cortex, the somatosensory cortex, all mapped on to the thalamus, and then winner-take-all strategies used to parcellate the thalamus. Diffusion-based methods exploit better contrast properties, and the reconstruction is pretty simple, typically clustering. However, the acquisition itself is low to medium spatial resolution, and there's poor anisotropy in gray matter, resulting in little noisy estimates of DTI, and finally, it produces a few clusters of nuclei as opposed to small thalamic nuclei. Another class of methods used for segmentation is functional MRI. In the left-hand side is a very similar method to the Barron's Atlas, where instead of using probabilistic tractography, they just did resting state connectivity from manually delineated cortical regions to the thalamus, and again, a winner-take-all parcellation strategy. Another very sophisticated method was used called instantaneous correlation-based parcellation by Manojkumar, and they, instead of a few 6 or 7 clusters, they have much larger number of parcels. Functional MRI methods exploit function instead of structure, and however, they suffer from low spatial resolution and distortion of the underlying API acquisition. The reconstruction is moderately complex, and they can produce vastly different number of clusters. On the left-hand side, there's like 6 or 7 clusters. On the right-hand side, there's like 20 or so clusters. Structural MRI-based methods are very popular. However, they've not been much used for segmentation because they have poor contrast properties. On the top left is the Bayesian probabilistic atlas, which is part of FreeSurfer, and uses a Bayesian estimate derived from pathology-based segmentation mapped onto MRI images. On the lower side, you can see another structural-based modality called susceptibility-weighted imaging, which essentially parcellates based on the susceptibility effect exhibited by different nuclei, which are different, presumably due to different ion concentrations. And lastly, on the top right is a multi-atlas based segmentation, which uses prior manually delineated atlases to segment white matter null NP-range data, which is slightly different from standard NP-range data. Structural MRI methods have the highest spatial resolution. They can go anywhere from 0.7 to 1 millimeter isotropic resolution. They have minimal distortion compared to the previous two methods we saw. However, the contrast is pretty poor on standard T1, and the reconstruction methods tend to be fairly complex. Here I want to show some multimodality-based reconstruction methods. On the top left is a reconstruction which uses multi-TI MP-range as well as SWI at 7 Tesla to look at different nuclei which get delineated at different TIs and also in the SWI image. The right-hand side is a improvement to FreeSurfer, where they have added DTI information in addition to the Bayesian model from T1 to produce much more accurate boundaries for the thalamus, especially for the ventral nuclei and the mediodorsal nuclei. And And lastly, um, uh, deep learning based methods have been used to synthesize white matter null MP range prior to segmentation because they are not commonly required. So here, this unit has synthesized white matter null MP range images from the standard T1 images and then segmented them. I want to talk a little bit about the technological breakthroughs needed. Nuclei granularity from in vivo imaging is still limited, even at 7T. We'd like to see subdivisions of the anterior thalamus. Newer image contrast, such as direct visualization, will permit subject-specific parcellation. DTI and fMRI at comparable resolution to structural MRI could remove discrepancies between methods. And finally, it'd be nice to have better, cleverer ways of combining modalities. And deep learning could help with all of the above using either contrast or super resolution. I'll leave with a few points to ponder. On the top left, we have multiple atlases, and they all are structural atlases, and yet the nuclei look pretty different. On the bottom is three different parcellations from structural DTI and resting state MRI on the same set of 20 subjects, all healthy young subjects. And you can see that the three state-of-the-art methods have fairly distinct looking segmentation. So the question is, which is correct? What I would like to leave today is the following things. We still need age stratified atlases. Most atlases currently have healthy normal adults. We need to look at the effect of lesions, which can affect registration in deep learning based methods. We have specialized sequences like white matter null MP range versus data in existing databases, which is the standard T1. So methods should be able to exploit just standard T1 as opposed to specialized sequences. And then we just talked about this, which method is more accurate? Is that even a good question? What does it even mean? Do functional methods have to respect structural boundaries? And then there's also a paucity of independent validation. Some methods have been validated and some have not. And then could we use clinical outcomes in hypothesis-driven experiments to assess accuracy? And lastly, the optimal method could depend on the application. So neurosurgery might prefer something as opposed to neuroscience or maybe radiology. With that, I'd like to conclude my small presentation and acknowledge a whole lot of collaborators. The ones in blue are actually all part of the Tango group. And I thank you for your attention.